working with a probability system, what is entropy? So if I could summarize it to an understandable definition, I think it would be something like how much information your system does not have or should have in order to have all the information to make the perfect decision, to know exactly what is going to happen and what is the best decision. So the easiest case would be well, a simple probability of a thing happening or not, so a binary option. And the entropy plot, if you go and see the entropy function, the entropy plot would be something like this. This is the probability of a certain thing happening, and this is the entropy of the system. What does this mean? So this is 0.5, and it's the highest point. If you are in a certain point of your life that you have no idea what is going to happen, you are here. You have absolutely no information, and you need the maximum amount of information to take the best decision. So to know that either this or this is going to happen. And what this temperature scaling is actually doing is saying the network trains, and if you look at its prediction, it says, oh look, I'm here. I'm at this point. But if you look at the calibration plots, they will tell you, well, you shouldn't be so confident. You are overconfident. We need to take it down a notch. What can you do about it? We can increase its entropy. We can decrease its probability as well. You can see this 1 minus this thing. Maybe I should do it on the other side. It's easy to understand. You say you are overconfident. You want to lower the probability of your things. So you want to move in this direction. So if you move in this direction, it will have a lower probability and it will have a higher entropy, which is exactly what they describe on the paper. So they say that this simple temperature scalar can move you around in this plot, in the plot of how much your system, how much information your system needs to have the perfect information. And with this simple scalar, you can correct the position in the entropy plot. And that's why they describe this so much in terms of entropy, which is very related to this other plot, which is called cross entropy. So not to go into too much details, but this thing from an information theory point of view makes a lot of sense. And questions, discussion?
So I was wondering at the beginning,
Yes.
you said there is a lot of ways to measure the calibration of your network.
Yes.
And I was wondering what are the advantages of each of the methods, when will you use the log likelihood, when will you use one distance or LTO?
So they decide to, in this paper, they decide to go with these, well, they are the same, but this one is more understandable in my opinion. This is the actual distance between the beams and the correct calibrated results. Which one is the best one? I really don't know how to answer that. I think it depends a lot on your application. Do you want to minimize your worst case scenario? Do you want to minimize the most common case is the square distance, the L2 distance. I really don't know which one is the best. They don't explain why they use this metric, as far as I remember. They just say that if you are very concerned with your worst case scenario, you should use this one. But I don't have a definite answer to that. If it was me, I would go with the square distance because it's well-rounded usually.
Yeah, like the thing I was thinking about is that so if you just want to minimize your log likelihood, for example, I don't really have to use fancy method. You can just do a logistic regression in the end, and you are done. This logistic regression, I think, is like going to learn to calibrate properly your network.
Mm-hmm.
So
That's Platt scaling.
Mm-hmm.
So that's exactly what the Platt scaling method does. It fits a logistic regression at the end to make sure that it is properly calibrated. But what they show is that it doesn't work as well as. But so the problem is that it also changes your most likely predictions, right? So it is going to affect accuracy. It is going to give you a good calibration, but it's going to affect your accuracy.
If you look at the temperature scaling, they also say that T is optimized with respect to the cross entropy. So you need to keep a validation set apart, and then to minimize the cross entropy on the validation set, changing the temperature scaling. Another advantage of this temperature scaling is that it does not change the model accuracy. So you can preserve the accuracy and optimize the calibration.
They do provide an explanation for that in the paper, which is that they say that the calibration problem in neural networks is a simple one. So you don't need all the parameters from the flat scalar. You can actually do, or from the matrix vector scaling, you don't need all those weights and biases. You actually need only one of those parameters, and that's enough to solve your problem. So this temperature scaling is actually a particular case of the matrix and vector scaling, which is a generalization of flat scaling. So you are effectively doing the same thing, just specific to these neural networks.
And it's two totally different processes. You train your network as you would normally. When it's trained, you take your validation sample, and you train only the temperature, the logistic regression,
Yes.
without touching the parameters, in
Yes.
fact. So, and then you just focus on calibration, essentially.
Yes.
Which is
Because
quite a
first
bit.
you maximize your accuracy, and then you know that you will not change your accuracy. So you maximize your calibration without changing the accuracy.
What's amazing is that you can separate the two, and it's still. I mean, that's what I find
Yes.
the most surprising, in fact.
You
That's,
can take your trained model and apply this like now. You just go home and code this, and it's good to go. You don't need to
just
train your model again.
as a layer on top. Yeah,
Yeah.
I think that's quite amazing.
Yeah.
So, I hate it.
You have
It feels like
okay.
such a fucking hack. Because it is, but it works.
Yes.
You've used this in practice. You use it in production. How does it compare to things that actually learn the distribution, like variational autoencoders or?
I didn't compare it with the other methods. I just used this as a hack, as you mentioned.
Is there any problem with there's a subset of your data space where, so that in minimizing the error, is it possible to minimize it in some part of the space and makes it worse in other parts of the space? Minimizing the EC
Calibration.
Yeah. As in when you're just using a one parameter fix.
Worse in what terms? What
As
metric
in,
do you define as worse?
Can it make it less because you're not actually trying to learn the distribution here, you're just
Yeah.
trying to tweak things to make it
Yes.
better.
Yeah, to make it fit.
Yeah. And you're only trying to minimize a single number.
Yes.
Is it possible, have you found that it makes it better in a large parts of the space, but where the calibration error worse in other parts of the space? Because you're only focusing on the global outcome.
I don't know how to answer that question. I would suppose that one problem with this is that you need to split your things in bins, and the binning process, you can do it like in many ways. So I suppose that there are cases, certain binning strategies that you might get worse performance in some bins after you apply the scaling. I suppose so, but I'm not
Is
sure.
the binning on the label space or on the data space?
The binning is on the softmax space.
Okay.
And you can choose any binning strategy you want. You can make like the first bin super small and the last bin super large. You can do whatever you want. Usually, it's either equally spaced in the softmax space, or each bin has the same number of samples, of softmax samples.